It's my pleasure again to introduce Jinming Wang. He will give the second part of the talk, a stable version of Gromov's angle shrinking problem and its index theoretic applications. Okay, Jimmy, it's all yours.
Thank you. Thank you for your introduction, and thank you for the invitation for the talk. So in the second part, I will explain more details for this angle shrinking problem, as well as index theoretic applications. So first, let me just quickly recall in this talk, I will mostly focus on the angle enlargement problem we used throughout our proof. So here, angle enlarging that we have a convex spherical polytope, call it Y, and we want to find a deformation of Y, and such that along the deformation, the dihedral angles becomes bigger than the original Y, and eventually it becomes a hemisphere. So in the hemisphere, all the dihedral angles are equal to pi. The boundary is smooth. Here in this last picture, the boundary is exactly the equator, and now all the faces become this equator face. Okay, so this is the angle enlargement problem we'll focus on. And also mentioned in Zhizhang's talk, in this picture, actually, in dimension 2 case, where dimension 2, Y is a spherical polytope, Y is inside the S2 inside R3. And in this case, the angle enlarging problem always has an affirmative answer. So this fact actually follows from a very elementary lemma from spherical triangles. So if you look at spherical triangle ABC in this picture, now we want to raise, say, these two dihedral angles, angle B and angle C, where there is actually angles. And we can always move the B a little bit and move the C a little bit so that, okay, we have a new spherical triangle A, B prime, C prime, and the angles all become larger than the original ones. Okay, this fact actually follows from the following fact that you start from the point B and point C, and then compute the angle B and angle C. Okay, this is a smooth map that actually one can compute the Jacobian. F, this determinant of df is actually non-zero. And with this non-vanishing Jacobian, you actually can move it, in whatever sense you want in the infinitesimal sense. But of course, this lemma only holds for spherical triangles, but not for Euclidean ones. Now, with the help of this lemma, we can really look at the general case. If you work on the spherical polygon like this ABCD, you see each edge lies in the triangle. Like, for example, edge BC lies in this large triangle. So this is because that spherical polygon has very simple combinatorial that every edge is only adjacent to two edges. Now, with the help of the previous lemma, we can move the edge BC a little bit. Well, in general, not necessarily move out, but, well, just move it so that these two angle B and angle C become larger. Okay, now you keep doing this, okay? And the process won't stop until all the edges are not movable. You see, if really we get some edge and move it until it's equal to pi, it's not movable. But when it's really pi, it will coincide with it's another adjacent edges. So we can always move it until every angle becomes pi. Okay, this is actually a nice compact argument because the space of all spherical polygons with a fixed number of edges is indeed compact because they're only given by finite many vectors. So you can always do this like step by step and have a limit. And eventually, the limit happens when all the angles become pi. Now it follows from the area formula that the area becomes 2 pi, which means it's exactly the hemisphere as indicated in the right picture. Okay, so this is one case that is doable in the lower dimensional. With 2D case, actually, this means that if you really work on the 3D problem where the spherical link is 2D, then, well, it's done. And another case we can think about is when our Y has exactly n faces as a spherical polygon in Sn-1 in Rn. And in this case, we call it simple. So in this case, while we have exactly n faces, and each pair of face will form a dihedral angle. They will meet, and if they meet at a codimension 2 face. And in this case, the angular longitude problem actually have an affirmative answer. So geometrically, as mentioned in Zhizhang's talk, Y is the spherical link of a manifold with columns. Here I've drawn an example of, well, it's indeed a non-example. Because this is a shape of a spherical polyhedron in S3, R4, which you cannot really draw it exactly. But as you can see at this shape has 1, 2, 3, 4, and 5 faces. So it's not simple, but at this point, you can look at we have face here and face here. They do not form any dihedral angles. Okay, so this example not simple, but for simple case, actually, the answer is yes. So this simple case really inspired us to talk about the algebraic version. So let me talk about really how to show the simple case. So if you work on a simple spherical polyhedron where we have the faces F1 to FQ, and I denote by V1 to VQ the inner normal vectors of the faces. So think about the polyhedron in Rn, and these are faces in Rn, then they're actually hyperplanes. And with them Q is equal to n, meaning simple. So now we want to deform the polyhedron, and equivalent to say, we just need to deform the vectors. Whenever you give the vectors, you determine the polyhedron. And now, to deform the vectors, we need to deform the Gram matrix, where G is the Gram matrix given by the inner products. So, of course, you have the vectors, the Gram matrix is completely determinate. But if you have the Gram matrix, then you can use polar decomposition to get back the vectors, only up to a unitary transform. And where the G is, well, if you're going to deform it, you have a path of positive definite matrices. Now, our condition on dihedral angles actually give the condition on Gram matrices. So we have the very nice formula, cosine of pi minus theta ij is equal to the inner product of vi and vj. So this means that we want to increase the dihedral angles. So equivalently, we're just going to increase inner products. And by our assumption, every pair of face will form a dihedral angle, meaning that all components in the Gram matrix are considered. So now we want to increase the dihedral angle, just need to increase the component, and we have a very simple formula. Just define the G of T to be 1 minus T times G plus T times W, where this W is a matrix of all ones. Okay, so imagine eventually all the faces become this one face, and all the vectors become one vector of the normal vector of the face, and the inner product will be all ones. And the linear algebra argument, we know that this path is always positive definite. And well, it's positive definite unless T equal to 1. And now you have the Gram matrix, you can get back the vectors. And then you get back the polyhedron. And as an example, there's a very nice classical paper of Coxter, and it gives the classification of polyhedrons where dihedral angles are less than or equal to pi over 2. And in this case, if all angles are not obtuse, then this Y is always simple. So the proof is actually very elementary. So if dimension equal to 2, well, it just follows from the area formula I just wrote. Well, this is actually a Gauss-Bonnet theorem. And because L angles are small, so we get a bound of the Q, where Q can only be 1, 2, or 3. Yeah, but, well, it should be 3. And in higher dimension, it's done by induction process. And also in the same paper, it tells us if you're working on the Euclidean polyhedron, then, well, it doesn't have to be a simplex, but it could be at most a product of simplex. So this gives an example of simple polytopes. It's very simple spherical polytopes. Okay, so any questions? All right, now I flip back one page. In this page, this gives us an idea. So just like consider the polyhedral is almost equivalent to consider those vectors. Okay, in the normal vectors. So we can form a so-called algebraic version of angular algebra problem. So we consider V1 to VQ. They're just some unit vectors in Rn. And we assume that there exists a vector, let me call it n, such that the inner product of n and vi's are all positives. Okay, now we gave a subset of the product of the two indices and we want to deform the vectors such that for the indices belong to a subset, the inner product become larger. Okay, just to the previous page, angle enlarging means inner product enlarging. But in this problem, so we call this algebraic problem because we're really doing linear algebra. Yeah, we're doing vectors. So the correspondence between these and well, this kind of version is actually strictly weaker than the original geometric version. Because during the deformation, you're actually forgetting the combinatorial type of the spherical polyhedral. So for the vectors V1 or VQ in the deformation, even if originally they're from a spherical polygon, but during the deformation, we don't require the form of spherical polygon. Or even if they form spherical polyhedron, then probably they have a different combinatorial type. Okay, so this kind of deformation really gives more flexibility to deal with the problem. And the correspondence between the two problems is that, okay, originally have angle enlarging, but now you're considering inner product enlarging, just as this condition that. And originally we're considering convex spherical polytopes, spherical polyhedrons, and we replace this condition by the existence of the vector n. So let me draw a picture. So above, this is spherical polytope, well, in F2 in R3. And we can pick the vector n to be any vector that points inward. Okay. So because it points inward, then as positive inner product with all the normal vectors. And during the deformation, we still assume that the deformation is near the vector n, so that the inner product is also positive. And I would like to mention that if we really work on a manifold with polyhedral boundary, as mentioned in Zhizhang's talk, and we assume all the dihedral selects equal to pi, and that this vector n actually can be globally defined as a smooth vector field. So you just choose any vector field that points inward. So locally, here, exactly the above picture is a vector pointing inward, but you can extend it smoothly. Just think about the vector that's, well, always like moving along the edge pointing inward, just as shown in the picture. Okay, so this is the algebraic version, but however, it's still open. We still don't know how to do it. But there's a very, very naive idea that we can really solve it by just simply raise one dimension. Okay, so here is the construction. We have the vectors vi, and we just add one extra dimension, add an extra vector w. Okay, and we'll do a linear combination and normalize it by adding t. Now we compute the inner product that will be given by this formula, and one can see directly that it's greater than the original vi convolution. Well, it seems that from this observation, the problem is solved, right? You just add a dimension, then everything becomes trivial. But this actually what we really want. Well, one reason is because it's too trivial, yeah. And you can see when t go to infinity, every vector concentrates to the extra dimension, where you will lose all the geometric information. And another reason is that if you think about this process geometrically, if you're working on a manifold with polyhedral boundary, you're actually this extra w, you are actually considering well m cross like C cross S1. Because this process will just introduce a new new direction and new vector W, and not introduce any new phases. However, if you take product with S1, you will lose the index information. Well, precisely speaking, the Euler characteristic. Okay, so that's not what we want to do. What we really want to do is to still keep the Euler stuff. So now let me give we think the right interpretation of the way to raise one dimension. So this we call a stable version. So still we work on the V1 to VQ, the vectors, and we have the vector n just as an analog of the convexity. And we add one dimension, work on Rn plus 1. And the W is a unit vector in the extra dimension. And now we want to deform the Q plus 2 vectors. Okay, we have the original vectors V1 to VQ, and with two extra vectors, W plus and W minus. Where W plus and W minus are originally plus minus W. Okay. Now during the deformation, we still want to increase all the inner products. So for these VIs, it's just become larger. And for the W, they also become between V and W, they also become larger. And well, they are originally 0. Okay. And we also need to have the N property. And after the deformation, they're all equal to the vector N. And the W plus minus this path of W plus minus get back to W plus minus. Okay. All right. So this is what I mean by the stable version. So let me visualize the stable version to you. So originally, let's say we have this picture and the two vectors. Okay, let me still draw a geometric picture. And what we do is to take a product with a closed interval, say 0 to 1. Now the W direction is just the extra direction of the new edge. Now with a product with interval of 0 to 1, we actually introduce the two new faces, this bottom face and this top face. Their normal vectors are just plus minus W. Okay. And these V1, V2 are still normal vectors of these two faces that introduced from the two original faces. Okay, so as you can see in this picture, we want to do angle enlargement for the right picture. And this means we have to do with this 2 plus 2 vectors, two original vectors as well as the two extra vectors. Okay, so if you really think of geometry, you have like a manifold M, and now we'll consider actually M cross the interval. And as you can see, if you do that, well, this will not affect the Euler characteristic. Yeah. All right, so that's the statement of the so-called, we state the stable version, and it turns out that this is correct. Okay, so now let me briefly tell you what is the construction of this new path is. So first, we fix a smooth path of vectors. We want to VQ that deform the vectors to N. And well, these vectors, of course, exist. It can be anything, yeah. We don't care about the dihedral angle or whatever inner product information, but we do care that these vectors all along the path, they have positive inner product with the vector N. So geometrically, you can think you have a spherical polyhedron, then you just deform it. Okay, then you just deform it to the hemisphere without any restriction, and this can definitely be done. Okay. Now, our definition of the new vectors is given by the following formulas. So for the VI tilde, it will be just a modification of the original VIT plus some extra W component. Okay, and here the coefficient, I call it PT, is carefully chosen by the above picture. And the W plus minus, this path is also going to change. We have the originally plus minus W, but plus the N here. Now, for the function p of t, we define it by the following picture. So first, from 0 to 1 minus delta, where delta is a very small number, and it's a function square root of c of t. And then, where c is a very large number. And then we arrive at 1 minus delta, and from 1 minus to 1, we just do a linear path. Okay. And this is the function pt. You can see we raise it, and then we have to go back. Okay. But for the function q of t, it's simply p of t times 2 over theta, where this theta is this inner product, the lower bound, positive lower bound of all the inner product along the path. Okay. Now with this definition, we can just sit down and compute the inner product. So the inner product, so first from between Vi and Vj, and we can sit down to compute that. The inner product can be, well, it's just Vi comma Vj t plus this pt square over 1 plus pt square. And when t is from 0 to 1 minus delta, the pt is just equal to square root of ct. So in this case, okay, let me just write here. In the first line, p of t is equal to square root of ct, so that we have just a ct here. Okay, now we want to get this new inner product is greater than the original. So from the first line, we want this hold. So just by, well, sit down and compute, you need that c to be greater than, well, this expression on the right. So we just need to c to be greater than the sup of that. But here we have t in the denominator, but that really doesn't matter because when t approaches 0, we assume that this path is a smooth path, so we're computing the derivatives. So that, well, this is a continuous function on 0 to 1, it definitely has a sup. And so this is the first part. And then for the second part, when t is greater than 1 minus delta, we just recall that in this case, t is almost 1. So that this Vi of t are already very close to n, which means their inner product are already very close to 1. But we're comparing this with the original inner product, but definitely they're fixed numbers, they're definitely away from 1. So we can always pick a delta such that the inner product of the VIT VJT near 1 is greater than the VI VJ. Okay. Now, with the help of this, we can look back at the formula. So this part is greater than VI VJ, and this PT is just PT, whatever PT, okay? This is definitely greater than the original VI comma VJ. All right, so this is the first part of the inner product of VI and VJ. And we will still need to talk about the second part, the inner product between VI and W. Okay, so just recall that we want the inner product, okay, we want VI tilde of T and W tilde prime minus of T to be positive, greater than 0, because originally they're 0. Okay, now we can just compute the inner product. It will be something positive times this. This is a VI of n, because when n there, over theta over 2 plus minus 1. And since the numerator is greater than theta, and we have this first term is greater than 2, and now 2 plus minus 1 is always positive. Okay, so that's what we did for the rest for the second part of inner products, but combine them all, we have proved this proposition. Okay, so this is actually a very elementary computation, right? But I think that really the hard part is that to figure out what the right interpretation of the inner product of the angular lambda problem that will be useful in the proof of the index theorem. Now let's come back and look at the index theorem. So here, for simplicity, I just assume that we're comparing two manifolds, where the second manifold M is a Euclidean polyhedral, convex polyhedral, and the manifold N is well, it's just a manifold with polyhedral boundary, and we have a map, spin map, with non-zero degree mapped to it. Okay. And we want to prove that if we have scalar curvature comparison, mean curvature comparison, and dihedral angle comparison, then we get all equal. And furthermore, this N manifold is also flat. It's also a convex Euclidean polyhedral. That's what we want to prove. Now, to prove this, we're going to use the index theoretical method. So we consider the bundle E to be the spinor bundle of the direct sum of the tangent bundles. And in this case, it's simply the spinor bundle of N tensor with the spinor bundle of Euclidean space. It's a flat bundle. And the D is the Dirac operator on this bundle. And here the boundary condition is given by this. It's also introduced in Zhizhang's talk. So on each face, we have the VI bar as the inner product of Fi. So let me write here. So this is inner normal of Fi bar, and this is the inner normal of the corresponding face Fi in M. Okay. So for this operator with this boundary condition, we can actually prove that the operator is well defined and essentially self-adjoint. And Fredholm, if we assume that, okay, the domain angles are all smaller than pi, and also we have the angle comparison, the product comparison. Okay, so here's the very important part. Although in the definition, originally the tau, everything are geometric, okay? But as also mentioned in Zhizhang's talk, for the second vector, we can make it more flexible. They can actually be any smooth vector field. Well, as Christina asked in the previous talk, for the first vector, well, there's no compromise. To ensure, even to ensure the formal self-adjoint, we have to assume it's the normal vector. Okay, the first vector has to be geometric, but the second vector, they can actually be anything. So we need to sit down and prove a new, prove this essential self-adjoint and Fredholm even for these vectors algebraically, they're from nothing, and the thing still works. And it turns out the condition imposed on the two groups of vectors are exactly the comparison of the inner products. Okay, so well, the first part is geometric, which we need the dihedral angle from the N part. It's really pi. This is geometric. But even if the second group of vectors does not form a real manifold with polyhedral boundary, we can still talk about the essential self-adjoint. Just need this inner product comparison condition. All right. So now our problem is well, let's assume for a while the inner product comparison is already satisfied. The other is already strict comparison. Okay. Then we just need to compute the index. To compute the index, our idea is to use a homotopic invariance. So originally, we have the data from N to M with polyhedral boundary. And the right part is something what we already know. It's written in the paper of John Lott, saying that if the manifolds are manifold of smooth boundary, then the index is null. Okay. In fact, it's equal to the degree of F times all characteristics of M. Here, M and M prime, F and M prime for the degree, and all of they're really the same because they're formed from deformation. Okay. And our idea is that, okay, we want to construct a deformation from the left-hand side to the right-hand side. But during the deformation, we have to assume the operator is well-defined anywhere, which means we want the dihedral angle comparison. Here I add a quotation mark because they're literally not really dihedral angle comparison, the inner product comparison. So when I say dihedral with a quotation mark, it means, well, the inner product formed by the vectors. But still, we only care about the vectors for the adjacent faces. Okay, now the question is, first, does the deformation exist? And second, if it exists, do we have index really equal? Now the first part, you can imagine that's why we care about the angle in enlarging things. We can, like, you have n and m here, you want to deform it. We can first enlarge the angles of m, right? Just enlarge it to be pi, just open it up, okay? And when I open the m up, now you can deform the n geometrically, okay? Now, and eventually, it becomes a manifold smooth boundary. So to guarantee, but so far we don't know how to do it geometrically, but we do have a stable version of the algebraic version. So if we take product of 0 to 1, and now we can apply our angular logic. Okay, I will explain this more in details, but you can see that that's why we really need this. But in the next few pages, I will pay a little bit attention to the second question. Even if we have the deformation, why do we have the index of the sim? Well, this seems a naive question, right? You have a path of Fredholm operators and a continuous change the index of the sim, but here in this problem, you have to prove that it's really a continuous change. Okay. But I just want to mention that although turns out in the full generality we're doing algebraic deformation, but if the dimension is equal to 3, or we're dealing with manifold with corners, the deformation can be done geometrically. This follows from the previous two examples I mentioned for spherical polygons and simple spherical polyhedrals. In these two cases, the deformation exists geometrically. But in general, we still don't know. Okay. All right. Now let's look at the index part. Still, we look at a 2D simple case. So the left picture is maybe you can think about the tau we start from. We have the two group of vectors, u1, v1 here, and u2, v2 here. And by up to some rotation, we can assume u1 equal to v1, but u2, v2 are probably different because the angle, well, they are strictly different. And now the boundary condition is given by this ui and vi here, where the ui are the normal vector of these two edges, but vi are some other vectors. Okay. Now we want to change the vector, change the boundary condition by changing the vectors. For the bottom edge, we just let this vi prime to be the same as v1, but for the v2 prime, it will be changed, well, slightly a little bit, okay? And well, even if you change the two vectors, v1 prime and v2 prime simultaneously, you can still do a rotation, so that becomes the picture of this. Now the new boundary condition b prime is given by the vector ui and the vector vi prime. Okay. Now, to talk about if the index is the same, we have to restrict our computation of index in the same space with the same boundary condition. So we can introduce a unitary that deforms that maps B to B prime. So you can see here, let me draw an arc. So along this arc is polar coordinate just theta from 0 to alpha. So at the bottom, v1 and v1 prime are the same. So it means you don't have to do anything, right? They're already the same. But at the top, v1, v2 and v2 prime differ by an angle, beta prime minus beta. So this means at this top, we need to rotate this picture a little bit by beta prime minus beta. Now we just need to define rotation. This is rotation by 0. This is rotation by beta prime minus beta. So that's exactly what it means here. Theta maps to this. Where the bottom here, you can say when theta is equal to 0 is no rotation. When theta is equal to alpha, it's rotated by beta prime minus beta. And now you have a rotation in the vector level, you just lift it to the spinner, and this gives us a unitary that maps B to B prime. But we need to notice that this unitary is not continuous at this origin. Because it's not a constant near theta, you say when r equals to 0, well, different direction have different limit. So this point is the singularity. Okay. Now we want to talk about the index of this operator D, and we change it, the Dirac operator, change it to polar coordinates, it becomes like partial r plus 1 over r times a, where a is essentially the Dirac of the Dirac operator near for theta. Now, obviously, index of d with the b is equal to index of u du star with the b prime, because u maps b to b prime. Now we can compute the u du star. U commutes with partial r because u doesn't have r, and then becomes 1 over r ua u star. And you compute the commutator. The commutator of u with d theta actually is not 0. It will involve a new term, essentially beta prime minus beta over 2 alpha, but we still have 1 over r here, so 1 over r. Okay, so these two equalities are almost trivial, but now the question is, do we have this equality? That's what we want to show, yeah? D with the b prime is equal to d with b. But now the operators really differ by a function, right? By 1 over r things. If it's a smooth function, bounded function, then we definitely know, yeah, they are equal. Just define linear paths moving one to another. But in this situation, it's not it's an unbounded function. 1 over r is unbounded near the origin. Okay. So, but fortunately, in this picture, is actually 1 over r is actually a bounded function in terms of the operator node. So let me state our let me call it 1 over r lemma. So consider manifold with a conical singularity and a conical operator like this. Then it's known classically that D is essentially self-adjoint near r equals 0 if and only if A has a spectral gap greater than or equal to 1/2. Furthermore, if A is strictly greater than 1/2, then 1 over r, the multiplication operator, is indeed a bounded operator from the domain of D to L2. Okay, and with this lemma, we can actually prove the index is the same because the homotopy argument now works. And to prove this lemma, one just need to find the parameters of D near r equals 0 and use the short test. Here I mentioned that this strict spectral gap is very, very important for this lemma. If the spectral gap is equal to 1/2, then the 1 over r will be unbounded. In fact, one can compute that the norm of the multiplication operator of 1 over r is about 1 over, well, spectrum A minus 1/2. Okay. All right. So now geometrically, we describe we can describe the spectral gap by dihedral angles. If we have strict inequalities of the quotation mark dihedral angles, meaning possible inner products, then it's equivalent to say we have strictly greater than 1/2 spectral gap. Okay, now with this 1 over r argument, we do have the index homotopy equivalent. Okay, but well, just in case you might ask, well, this is just 2D case. What about higher dimension? In higher dimension, like say this in 3D picture, we will definitely still, if we do the deformation, we'll definitely still have a 1 over r, where r is the distance to the origin. R is just a distance to the vertex. Okay. But during the deformation, you might also change the dihedral angles. So for example, the angle here. When you change it, it will also introduce the unbounded term. Let me call it S, where S is the distance to the edge. Okay. The two terms will appear simultaneously in the deformation. And which means the error term is about, like, at most 1 over r times 1 over s. Okay, it's really unbounded in two different directions. But fortunately, this operator is still, with this modification, is still a bounded operator. This is what we proved as a higher dimensional analog. So if we assume the strict equality of dihedral angles, well, quotation mark means, well, possible inner products, then the multiplication of this function is a product of the distance from x to all the sigma k. Sigma k is a codimension k skeleton, where k is from 2 to n. We'll start from the codimension 2, codimension 3, codimension 4, and even higher. And then we'll multiply them all together. It's still a bounded operator. So this means even a higher dimension to do the deformation, it will involve some error, unbounded error term, but still a bounded operator. Okay, but then the proof is essentially, well, essentially the same as the previous 1 over r, or just use the 1 over r things. Okay. All right. Now with all the ingredients collected, we are really able to state how we prove the theorem. So I will divide the process into several steps. So the first step, or the 0th step, let's assume for a moment that the comparison of the dihedral of the two manifolds N and M are strict. Okay, this may not be true, right? In the original statement, they probably equal somewhere, but let's assume for convenience for a moment that they are already strict. Now, the first step is that we take a product with interval 0 to 1. And we deform m times 0 to 1 to some m1 times 0 to 1. But we're not deforming it geometrically. We're actually deforming only the vectors. So during the process, this is just the algebraic deformation. The vectors during the process may not really come on genuine manifold of polyhedral boundary. Okay. And our goal is that after this deformation, this M1 will have product structure near every singularity. And also, it will have dihedral angle smaller than, but very close to pi. So because it's large enough, then we can do the next step. Okay. All right. So during this step, we need the stable algebraic angle larger, and to guarantee the index is constant, we need 1 over r lemma. Now, after the first step, you keep in mind that angles of M are already very, very, very large. So whatever you do on N, it will not affect the comparison of dihedral angle. So now we can just be very happy and deform the N to N1 geometrically. So keep in mind, in the boundary condition for the N vectors, no compromise, they have to be geometric, and that's where we can do. Okay. And this N1 will have product structure near every singularity. And after that, during the process, the index is constant because of the 1 over r lemma. Okay. Now after the second step, the third step is that we will still want to compute the index, and in the case that when N and M are already very, very the same, very alike. So we can deform the vectors from the M1 to M2 so that the dihedral angles, or even the entire geometry of M2 are greater than, but close to the N1. So this process is done by reversing our angle enlarging proposition. So start from the N1, you can, of course, enlarge it to almost become pi, but now you can think about the terminal for the near pi case is just the M1, but now we reverse the path. We go back from pi to the N1, and along the path we always have inner dihedral greater than the N1. So that's the reverse step, and also guaranteed by the stable algebraic angular enlarging. And during the process, the index is constant because of the 1 over r. Okay. Now the final step is to compute the index. We compute the index by a cut and paste formula, which means if you have a manifold with even polyhedral boundary like this, okay, and here we just be simple, like near this edge where we cut, everything is like product structure. So we can cut it away, right? And here, let's say the boundary condition gonna be some B and B here. And when we cut, we have B, B, and B, but this blue edge has to be orthogonal complement. This cut and paste, this green index formula still holds. Well, it's just follow exactly the same argument as for manifold with boundaries. Okay, And Gromov means that if we want to compute this index, is equal to the sum of the index of 2 parts. Okay. And if we're able to compute this part as index 0, then we can replace it by a smooth piece in this picture. And we can also compute this index is 0. Okay. And now we glue it back, and now it really becomes a smooth manifold with smooth boundary. Okay. So here, these two indices are computable because, well, in this case, the N and M, after the so many deformations, they are really product structure, and they are very, very almost the same near the singularity. So because they're almost the same, that we do know that we can really sit down and compute the index by the Bochner formula. Okay, now for the last picture, the index is known by the result of Zhang. All right, so I think I still have only a few minutes, so let me in the next few steps explain the step 0. Okay, a step I say, well, assume for moment is strict, but how do we deal with the general case? It actually follows from approximation lemma. Okay, so let me just first state the lemma. So we have a manifold with polyhedral boundaries. It's just the n cross 0 to 1 with boundary condition like this. And on this manifold, we have a Bochner type formula where this is the Dirac term is equal to the gradient plus some curvature term, and the boundary will be some second formula term. And there, in general, there will still be a boundary Dirac term, but it will be killed by the boundary condition. We only want this hold for any H1, so nothing to care about the essential self-adjoint. And now the K condition that we want this R to be non-negative and H is a non-negative. So for example, these two conditions are guaranteed by our geometric assumption for scalar curvature and mean curvature. Now, if we have a path of boundary condition B of t, okay, where the first part of the vector is just the same, but the second part we have some VIT, where the VIT could be, well, it can be anything, just not necessarily geometric, but we assume that they will converge to VI in C1 node. And the second condition that for each t, there's a non-zero solution phi of t such that to d such that d phi t is 0 and satisfy the boundary condition in the H1 space. For example, this is guaranteed by our previous arguments. So we have known the index is non-zero, then we have to have a solution. Then there's really a genuine solution phi for the original boundary condition, such that d phi is equal to 0, and also follow from the Bochner phi formula that nabla phi is 0. In fact, this phi is the limit of the sequence of solution phi t. In general, without this crucial condition, we only have the weak limit of the solutions. But with the condition here, we do have a strong convergence. So phi t will converge to phi, at least up to subsequence, converging in the H1 node, so that we have the d phi is equal to and number phi is 0. So yeah. So, and I want to emphasize that this lemma has nothing to do with the essential divergence of Fredholm. Everything is taught within its H1. So, and equivalently, we can just reverse the statement. If in the limit case there's no solution, then also in the nearby cases there's also no solution. All right. Now with the help of the approximation lemma, we can really deal with the step 0. Also use the angle enlarging process. We can deform the vector from M to some MT that increase the dihedral angles, and they are greater, but very close to the original M. Now when t equal to 0, it will converge to the original case, to the original case. But for t equals 0, actually we don't know how to compute the index. Well, the index, we even don't know if the index is well defined. But when t is greater than 0, because now this inequality becomes strict. So we can compute the index and get non-zero and get a non-zero solution. Now the limit will give us a non-zero solution for the original problem. And the existence of this MT also follows from the angle enlarging proposition, because we have to assume all angle become large. Okay, so that's maybe let me skip the proof of the proximal lemma and just say example time. So I just thank you to everyone.